Peter, thank you very much for your introduction, and thank you to the RSC Historical Group for inviting me to give this lecture today. I've been studying the history of chemical industry in the 19th and 20th centuries since around 1980. At one stage, I was involved with the University of York program for science education. Later, I joined the Edelstein Center at the Hebrew University, where I became the deputy director. The special interest at the Edelstein Center was a library which contained a vast amount of books dealing with the history of the dye industry. And my specialty was the synthetic dye industry, which I studied for about 15 years. And about 7 or 8 years ago, after doing some work on the history of civil engineering, Peter Morris invited me to work on the synthetic ammonia industry, which ended up with a monograph published by Springer in 2018. Since then, I've been developing that theme, going beyond 1940, which I studied until 2018, until the present time. Now I'd like to discuss. I'd like you to join me with my lecture on this topic, and let's see if we can all share. Okay. Right, the synthetic, a century of the synthetic ammonia industry, 1921 to 2021. I just want to get rid of more, excuse me. Okay. Got rid of the floating controls. Reading the UK newspapers over the last few days, one might get the impression that the pubs are about to run dry and supermarket shelves about to become emptied of food, the food to be replaced by decorations for Halloween and Christmas. Well, what is all this commotion about? I need hardly ask this audience. It's about the closure of 2 ammonia factories, both owned by CF Industries, one in Teesside and one in Cheshire. There is also the likelihood of another UK factory being closed. It's owned by Yara of Norway, which is about to reduce 40% of its European production, including at Hull. Okay, running out of gas. This is the story. It's a story of the shortage of carbon dioxide that is available from the synthetic ammonia industry. Teesside Live yesterday announced that Downing Street is working with CF fertilizers as meat manufacturers hope and pray. CNN yesterday featured a photograph with a caption, "Shelves usually stocked with chicken stamped empty at an Asda supermarket on September the 19th in London." Well, this is all about the cost of natural gas, which represents 70 to 85% of the cost of producing synthetic ammonia, and right now, perhaps a great deal more. And I should point out that this is not a new problem. In America, for example, around 2000, high gas costs caused closure of several ammonia factories, some of them permanently. And it's interesting that normally in the media, the ammonia industry is normally discussed within the context of its carbon footprint. Carbon dioxide from generation of hydrogen represents more than half of the carbon dioxide produced and emitted during the industrial synthesis of ammonia, unless, of course, it is captured and supplied to the food and beverage industry, which is the situation right now, as we've discovered. Now, at this point, I'm going to leave the politicians and world leaders to discuss the problems of the environment and energy supplies and move on to the main part of my talk. But every year, almost 200 million tons of ammonia are synthesized. 70 to 90% as required is converted into nitrogen fertilizer, such as urea and ammonium nitrate. The equation for synthesis of ammonia, often called nitrogen fixation, is in some ways deceptively simple. However, in order to overcome the low equilibrium concentration of ammonia, the synthesis requires a high pressure, a high catalyst, and a high temperature. In addition, a vessel that will withstand the brute force conditions. The synthesis also requires pure gases. The method of synthesis was developed in 1909 by the German physical chemist Fritz Haber at Karlsruhe. This is the laboratory apparatus of Fritz Haber. At the left-hand side is the converter or reactor where the reaction took place. The yield at in Haber's time was around 5 to 8%. And he realized that if he was going to come up with an invention that might be of industrial use, it would be necessary to recover or recycle the unused gases. As a result of which, he devised a process in which, after reaction, the mixture of gases was dried, liquefied, and the ammonia runoff here at the bottom, and the gases recycled through various pipes via a circulation pump back to the converter. As a result of which, this became a viable or potentially viable method for producing synthetic ammonia. Haber's work was financed by the Badische Aniline und Sodafabrik, or BASF company, of Ludwigshafen, seen here at top right, almost opposite Mannheim. Carl Bosch and colleagues at Ludwigshafen developed a manufacturing process based on Haber's method, and in 1913 completed the erection of this factory, which actually began production of synthetic ammonia in September of that year. The Haber-Bosch process, as it was called, evoked tremendous awe and attested to a great deal of scientific and technological creativity, in addition to its perseverance and courage required. It required design of a novel centrifugal compressor working at around 250 atmospheres, a massive converter suited to the production of a large amount of ammonia, and process control instruments. Coal was the source of power and of nitrogen and hydrogen. BASF originally sold the synthetic ammonia as a refrigerant. It soon, however, began promoting ammonium sulfate fertilizer. However, within a year, the First World War began. The synthetic ammonia was requisitioned for military purposes, the manufacture of explosives. So much ammonia was required that the Prussian government funded BASF, which constructed this vast factory at Merseburg near Leuna in central Germany in 1916-1917. Of this Haber-Bosch process, an Allied investigator stated that it was probably the most phenomenal scientific development up to date. The journal Chemistry and Industry was impressed by the brilliance of the application of physical chemistry. Well, this brings me on to the three main topics that I would like to discuss today. The growth of a global ammonia industry, which began 100 years ago in 1921, the feedstocks for producing hydrogen, and the development in the 1960s of single-train energy integrated units and their role in the Green Revolution. After the war, BASF refused to license its process. The need elsewhere for self-sufficiency in nitrogen drove research into high-pressure ammonia technology. Failure in Britain at Billingham in the northeast led Brunner and Company to acquire by industrial espionage details of the Oppau and Merseburg BASF installations. This is the Billingham factory. It opened in 1924. 2 years later, Brunner became part of ICI. And in 1928, a visitor stated that Billingham was a triumph of British technical achievement, despite the fact that it relied on stolen German technology. As we can see here in the bottom left, there were 3 units, each capable of producing 165 tons of ammonia every day, much of which was converted to ammonium sulfate, mainly for the export market. There were other ways of breaking the BASF monopoly. Thus, Giacomo Fauser in Italy worked on 250 atmospheres and developed a successful process by around 1921. However, until the mid-1920s, it was restricted to Italy because it had been acquired by the Montecatini Chemical Corporation. George Cloud in France worked at 1,000 atmospheres, achieving a higher yield. However, until the mid-20s, he had problems with his converter shell, which tended to explode. And thirdly on this list, we have Luigi Casale in Italy, who worked at 850 atmospheres. He devised a very successful process that became available to all who wanted it in 1921, of course, at a cost. This is Luigi Casale. He set up his business, Ammonia Casale SA, in Lugano, Switzerland in 1921. He received considerable financial backing and soon went off to find potential licensees. This is Casale's process, not altogether different from Fritz Haber's method. Here we see the converter at the center. To its left is an ejector, which replaced the circulation pump used in other processes. The advantage of the ejector in those days is that it involved no moving parts. At left is the compressor, bringing the gases to 850 atmospheres. To the right of the converter, at F, is a tank through which tubes pass containing the reaction mixture. Under these conditions, the ammonia liquefied and was collected at G, and all the other gases, unreacted gas, was returned to the converter. Casale did most of his development work at the industrial city of Terni, which was northeast of Rome. Here we see a Casale converter being constructed at the Terni steelworks. Notice the giant bolts which were required to hold the lid firmly in place. No less important were the compressors. The firm of Binoni in Firenze developed the compressors shown here around 1922, specifically for the Casale process. Well, in 1921, Casale's process was available for licensing. His company supplied Italian-made machinery to all his licensees. This was very important since there was no other similar machinery readily available. As a result, during 1921-1923, Casale had a head start in the international availability of high-pressure ammonia synthesis. His first client was Noguchi Shitagao, a Japanese entrepreneur who, on the island of Kyushu, opened 2 factories, one at Nobioka in 1923 and another at Minamata in 1926. At the end of the decade, he began construction of a massive factory at Hungnam in Japanese-occupied Korea. Here we see several converters ready for inspection by the Emperor Hirohito. These were new converters brought in to supplement the output of the existing converters at Minamata. This is the Hungnam factory in Japanese-occupied Korea. It was one of the largest chemical factories in the world, and the output of ammonia was 480 tons per day. The method of control of a synthetic ammonia process was very different to the method of control of any other chemical process that had come before. This is the control area showing the switches and various dials and gauges for controlling and monitoring temperature, pressure, and gas flow. There was also above a very finely detailed graphic panel, enabling the operators to understand exactly what was going on. Controlling the ammonia plant was very much like controlling an electrical power plant. And one engineer observed it would almost appear as if chemists had solved the nitrogen problem so successfully as to render unnecessary the employment of members of their own profession, at least in the manufacture of ammonia. I pointed out earlier that the product from the Casale process was anhydrous liquid ammonia. The Haber-Bosch process produced a gas that had to be treated by refrigeration to provide anhydrous liquid ammonia. That was quite an expensive add-on. The synthetic ammonia industry was opened a little later in the United States. In 1928, DuPont at Belle in West Virginia opened this factory. It had begun a few years earlier using cloud technology, but had lots of problems: low yield, exploding converters, fatalities, so many difficulties, in fact, that in 1927, DuPont acquired access to Casale technology. And from that time, this was a successful factory. The other major factory in the United States was that of Allied Chemical and Dye, which also opened in 1928 in neighboring Virginia. Both factories relied on coal for producing nitrogen and hydrogen. The most important innovation that came out of research in the United States was that of the Nitrogen Engineering Corporation, founded in 1926. This is a typical converter of the era, showing all the various tubes required for cooling purposes and also as heat exchangers. Very successful converter that was installed in at least 100 cases in the following years. Nitrogen Engineering Corporation was acquired by Chemical Construction Corporation, known as Chemico, in 1930. It was eventually sold, soon after it was sold to American Cyanamid Company, but still traded as Chemico. By 1928, there were 8 novel processes, all based on high pressure reaction. Excuse me for my occasional pauses, but I keep getting lines of people coming into the meeting. And my apologies if you're also having this problem, but I'll do my best to minimize them. Okay, that should be a bit better. Okay, well, as a result of all this excitement in this brand new high-tech method of making ammonia, there was eventually, and not long after, a problem of excess capacity, even before the Wall Street collapse of 1929. As a result, output and prices were increasingly dictated by an international cartel dominated by the leading exporters, Germany and Britain. This could not include the United States as a result of the Sherman Antitrust Act, nor did it include Japan. The Japanese were not very interested in joining, at least until the mid-1930s, when they gained access to Haber-Bosch technology. However, although there were problems in many countries, this did not affect those nations that were involved in central planning. The growth of the ammonia industry took place mainly in Italy, the Soviet Union, and Japan, particularly in Korea. It was in these countries, as well as in Germany, that ammonia production was encouraged for maintaining national security in food and munitions. Germany adapted Haber-Bosch technology to the high-pressure manufacture of gasoline from coal. Here's an example of central planning. It's Mussolini's Battle of Grain, inaugurated in 1925. Here we see Mr. Mussolini driving a Fiat tractor. Once he's plowed up the land, then the Montecatini supplied nitrogen fertilizer made by the Fauser process was added to the ground. There was also the Soviet first 5-year plan of 1928-1932. This involved the import of Fords and tractors, electrical machinery, and American, German, and Italian nitrogen technologies. a lot of this was paid for in terms of wheat, particularly as it was available from the Ukraine. Now we move on to pure hydrogen and its production for a global industry. Originally, hydrogen was made by electrolysis, at least until the early 1900s, but it wasn't required in a very large scale. Production of hydrogen on a large scale was a consequence of the emergence of the synthetic ammonia industry. Fauser and Casale developed processes for manufacturing hydrogen by electrolysis, but this required a cheap source of hydropower. These are the electrolyzers in a Spanish Casale factory, beautifully lined up, producing all the hydrogen that was required of high purity for the factory. One advantage of the electrolysis process was that it could be switched on and switched off at will. However, most hydrogen was obtained from coal, particularly in the large factories. Incandescent coke was treated with steam to produce water gas, a mixture of carbon monoxide and hydrogen, known as synthesis gas, or more commonly, syngas. In the ammonia synthesis, carbon monoxide is a problematic catalyst poison. The Bosch-Wilde process, developed in 1915 at BASF, involves steam treatment over a catalyst to convert the carbon monoxide and hydrogen into a mixture of carbon dioxide and hydrogen. This is the shift reaction and is still in use, as we know to this day. Carl Bosch, in his 1932 Nobel Prize, observed that the procurement of hydrogen is the largest item in the prime cost. Conversion of the ready-made gas mixture into ammonia is only a minor cost factor. In America, around the same time, Charles O. Brown of the Atmospheric Nitrogen Corporation, a division of Allied Chemical and Dye, noted that the development and purification of the hydrogen is still the outstanding feature of cost and extensiveness of plant equipment. Hydrogen also became available from coking oven gas. This was important in Europe from the late 1920s. However, it was not taken up, at least before 1940, in the United States. Methane was also used occasionally in the United States and in Russia. However, the main work on methane and similar hydrocarbons was undertaken at Billingham by ICI. Billingham worked on the hydrocarbon off-gases from coal hydrogenation. It had taken up the German process of the late 1920s. Billingham treated these off-gases to steam reforming and found that it could produce quite good yields of hydrogen. The process was perfected by 1936. It involved heating hydrocarbons in the range 700 to 1100 degrees in the presence of steam and a nickel catalyst. The hydrogen and carbon monoxide formed were then subjected to the shift reaction. And this was applied to natural gas as well as various other off-gases. There was not a great deal of interest in this process in the United States, nor in Germany, at least until 1940. With the outbreak of World War II, ICI sent a group of engineers to Canada and the United States to assist in the erection of factories capable of producing ammonia from natural gas. The United States government sponsored the construction of 10 ammonia factories, 6 of them based on natural gas. This is the largest factory at El Dorado in Arkansas. After the war, it became the property of the Lion Oil Company. Notice the 4 buildings in the center of the picture. In these buildings, the reforming of methane took place. And this is what was going on in that factory. Notice that the production of ammonia at the bottom right takes up a relatively small part of the factory. The main part is involved in the production of the pure gases. Well, the ICI work involved primary and secondary furnaces. In the primary furnace, the methane was treated with steam under conditions that I just mentioned, producing carbon monoxide and hydrogen. From there, the mixture was sent to a secondary furnace for secondary reforming.
I'm completely jammed.
There was a slight disturbance, but I'll continue. Okay, in the secondary furnace, air was admitted. The oxygen in the air enabled complete conversion of the methane into carbon monoxide and hydrogen. And of course, the nitrogen was carried through for use in the synthesis. And all the rest of this plant, right up to the converter, was involved in the preparation and purification of these gases. This is actually based on the Nitrogen Engineering Corporation process that was used in the El Dorado factory, and as the process I mentioned earlier, which was the most successful American process. Well, as a result of American involvement in the manufacture of ammonia after the 1940s, the United States was the leading global producer. The original major factories at Virginia and West Virginia of Allied Chemical and DuPont were based here. But notice that the industry has begun migrating to the Gulf of Mexico because of the availability of natural gas and oil. And the transportation network of the United States was sufficiently organized that it was possible to quickly deliver fertilizer or ammonia to, for example, the Corn Belt in this region. This was a situation in 1955. There were 50 factories in operation or under construction. Part of the expansion was as a result of the war in Korea. Within the next 2 decades or so, the number of factories in the United States would double. Well, that's the situation around the 1950s. Within a few years, there was a demand for high-capacity, energy-saving ammonia units. The synthesis trains, or loops, up till that time were driven by reciprocating compressors, which accommodated relatively small volumes of gas. The limitations of these compressors made it necessary for large ammonia factories to operate batteries of ammonia trains. Here we see another example, in fact, of a Casale process with 3 compressors, each one for driving one train. And many of these compressors were still at work over 50 years later. Well, we move on now into this era of change, which involved the refining and combining of new technologies. Foremost among the engineering contractors involved was M.W. Kellogg of New York and later of Houston. Kellogg was one of the firms that built the government ammonia factories in the United States during the Second World War. There was also an increasing involvement of petrochemical corporations. Kellogg also studied improvements in steam reforming, in particular pressure steam reforming of natural gas. The primary reformer in this case was fed with natural gas as it was usually available under a relatively high pressure. This reduced by 25 to 35% the compression required for the ammonia synthesis. The process was also investigated and vastly improved independently by ICI. Well, as a result of these new developments and the need for high-capacity ammonia units, it was also necessary to invent or reinvent the converter. Until the 1960s, most converters had a maximum capacity of 250 tons of ammonia every day. Until the 50s, in fact, converters were practically all tube-cooled with a single bed of catalyst. This arrangement did not suit large, high-capacity vessels because the number of tubes would become excessive and the tube sheets required to hold those tubes would become extremely large and thick. As a result of this type of consideration, early in the 1950s, Kellogg introduced separate beds of catalyst with interbed cooling from quench gas. Here's an early Kellogg converter. Notice that instead of one bed with lots of tubes running through it, we have separate beds or baskets of catalyst through which quench gas is passed. This enabled the construction of much larger converters. Kellogg also took an interest in the use of centrifugal compressors in the ammonia synthesis. They were introduced into a number of ammonia factories for some of the operations, but not for all the operations. Kellogg was extremely ambitious at attempting to use a centrifugal compressor for controlling all operations in an ammonia train. And I should point out, centrifugal compressors had developed considerably as a result of developments in aeronautical engineering during the Second World War. And this led to the single train energy integrated unit capable of producing 1,000 tons of ammonia every day. This happened when, early in the 1960s, Kellogg brought together several innovations, most notably the single centrifugal compressor for one train and steam reforming under pressure. This tripled the rated capacity of individual synthesis trains. It brought about savings in energy and reduced by half the cost of fertilizer. The first order for one of these trains, in fact, for 3 of them, came from ICI at Billingham. ICI ordered 3 of these trains. The combined capacity was 900,000 tons a year of ammonia. They were meant to be ready for operation in 1966, but ICI had a few problems which delayed the opening or the inauguration for at least a year. The delays in completion at Billingham were ascribed to difficulties in procuring equipment due to a surge of ordering from all other chemical companies, or shoddy subcontracted engineering. As a result of this, credit to the first single train ammonia plant that, with a capacity of 1,000 tons a day, went to Coastal Chemical Corporation of Yazoo City, Mississippi. I find this advertisement extremely useful because it shows a photograph of the single compressor, the single compressor which drove a single train, the single ammonia converter driven by that train, capable of producing 1,000 tons a day, and of course, the single reforming furnace, which was not unlike the furnaces introduced during the Second World War. Other engineering companies got in on the act very quickly. One of them was Bechtel, which introduced a radial flow reactor. Up to that time, all the reactors involved axial flow. And this was based, I believe, on work undertaken by the engineering contractor Haldor Topsoe in Denmark. By the 1950s, urea was an important fertilizer, supplementing ammonium sulfate, which was going out of fashion, and ammonium nitrate. As we know, most of the carbon dioxide from fossil fuel-based ammonia processes is released to the atmosphere. This was in fact the case until around 1950, and in fact long after in many countries. However, increasingly from 1950, the carbon dioxide was captured and reacted with ammonia under a high pressure. Heating the ammonium carbonate so formed gave urea. Again, I'm sorry, I'm getting various lines coming on. I'm trying to remove them as best I can. Okay, so urea was an important fertilizer from the 1950s, and it still remains an important fertilizer. But the important point within the context of what's happening in the last few days is the necessity of capturing carbon dioxide for use in processes beyond straight ammonia synthesis. 1960s, this was the era of the Green Revolution. The global map of the synthetic ammonia industry was completely withdrawn during this time. There was increasing demand for fertilizers, stimulated by the introduction of the new high-capacity ammonia technology. We move on our global journey now to India. In the early 1950s, Prime Minister Nehru called dams and steelworks temples of modern India and encouraged their construction. Soon added to this category were the nitrogen factories. This is a situation in India in 1965. 21 factories in operation or under construction. Some of them were not very efficient. Some were quite large, such as number 1 at Sindri. This was a substantial factory. In fact, it had been suggested by British engineers in the 1940s before India became independent, and it was chosen as an important site for construction of an ammonia factory. Factory number 2 at Nangal, incidentally, relied on hydroelectric power for producing hydrogen. Well, this was 1965, temples of modern India, although I'm not so sure that all of them really were temples at that time, at least. This was a problem year for India. The failure of the monsoon took place. It was the first failure since around 1905. The same thing happened in 1966. There was a desperate need for famine relief and foreign aid. As a result, in 1965, 600 shiploads of wheat were sent from the United States to India. However, in 1966, there was an interest in ordering high-capacity ammonia units. These, with new strands of wheat, as developed by Norman Borlaug and colleagues, transformed the agricultural industry of India. I should also point out that industry also required at the time improved distribution networks and the extensive digging of deep wells for making available plentiful supplies of water. Hydrogen in India from around 1960 was based on a process developed by ICI involving the use of the light distillate naphtha. In fact, it was used extensively until the early 2000s. India increasingly from the 1970s began to rely on natural gas, which became the dominant feedstock from the early 2000s. Well, all these were wonderful achievements, but nevertheless, the farmers had to be taught how to use these new fertilizers. Studies on soil had to be undertaken in different climatic conditions. It was not altogether different from the 1930s, when companies such as ICI set up agriculture research stations. This sort of work and encouraging farmers to use these fertilizers, which was not always necessarily the case, is what transformed the Indian agricultural industry. Ping-pong diplomacy, the United States and China. In 1972, President Nixon traveled to China, where he met with Mao Zedong and Premier Zhou Enlai. This was, in part, an attempt to get Chinese to influence Hanoi and thereby bring an end to the war in Vietnam. That did not work out. However, this opened up China to the West and vice versa. The People's Republic of China ordered 13 ammonia urea complexes, 8 of them from Kellogg, all involving 1,000-ton-a-day single-train ammonia units. This was described as the largest dollar volume ever placed by the People's Republic of China with a US firm in the industrial sector. In fact, the combined size of the Chinese orders was unprecedented in the history of chemical industry. Not long after, President Nixon visited the Soviet Union. As a result of this meeting, again, in part aimed at bringing an end to the Vietnam War, and again, not successful, there was a further opening up of technology from the rest, insofar as American high-capacity ammonia technology was transferred to the Soviet Union, paid for with Russian ammonia and urea. Around this time, there was also the oil crisis. The oil crisis dominated the 1970s. However, even before the 1970s, there were concerns in the United States over shortages of natural gas, which many specialists believe should be conserved for domestic use. There was a great deal of effort put into return to coal-based processes for production of synthesis gas, but this petered out in the 1980s. ICI at Billingham was fortunate insofar as it had access to North Sea natural gas. In the mid-70s, America was in the middle of a major slump. However, the Wall Street Journal of December 1974 decided to cheer its readers up with a note that no slump here, builders of ammonia plants benefit from global demand. At this time, the worst economy since the Great Depression, American engineering contractors were involved in 12 ammonia projects in the Soviet Union, 9 with Kellogg, and 3 with Flour Corporation of Los Angeles, in addition to the 8 projects in China. This was quite an achievement and certainly kept a lot of people at work. The 1970s also saw Kellogg involved in assisting Middle Eastern countries develop their petrochemical industries. Iran, for example, in the early 1970s, ordered an ammonia urea complex, also based on the 1,000-ton-a-day ammonia single-train unit. And in 1975, a repeat order arrived. This had a tremendous influence on the development of chemical industry in the Middle Eastern countries, and still does. We should also mention developments in catalyst. One of the leading companies involved in catalyst research was ICI. ICI in 1940 opened a factory in Clitheroe, Lancashire, for producing large amounts of catalyst. A lot of its catalyst went to Kellogg for use in the Kellogg processes. This catalyst, 32,4, was used for removing of sulfur compounds from natural gas and naphtha. Nowadays, this work is continued by Johnson Matthey, also at Billingham. There was also a great interest among academics in catalyst research at this time. Gerhard Ertl and colleagues began to study the take-up of nitrogen at the surface of the iron catalyst as used in practically all the ammonia processes. He established that the rate-limiting step was the dissociative chemisorption of nitrogen. As a result, the mechanism of the process taking place in the industrial converter was established. As a result of this and similar work, Ertl received the 2006 Nobel Prize. There were further improvements in ICI's work on ammonia processes. This is the AMV process, first announced in 1983, and it summarized some of the points I've been making earlier. The treatment of natural gas for removal of sulfur, the methane then being transferred to the primary reformer, where in the presence of steam, the monoxide and hydrogen are formed. This mixture with unreacted methane then moves to the secondary reformer, where in the presence of air, the methane is completely oxidized. Then the shift reaction, which leads to the production of carbon dioxide, which is removed. The nitrogen and hydrogen with small amounts of residual carbon oxides was then subjected to methanation, a process developed in the 1960s. The resulting nitrogen and hydrogen were then led on their way into the ammonia synthesis cycle. Well, the 70s and the 80s, for that matter, were a period of expansion and contraction, as we've seen. Massive investment in fertilizer capacity in the Soviet Union, China, and India. In the 1980s, especially, the US and Europe suffered from overcapacity and lowering of prices, rather like the late 1920s. The problem in the US is that it was importing cheap ammonia from Trinidad, USSR, and Mexico based on its own technologies. The erosion of profit margins became a major problem. Nevertheless, demand for ammonia continued. but the industry was then suffering from inefficient plants. Heavy capital investment was required to replace outdated and worn-out equipment. This provided an incentive for a new area of investigation in the ammonia industry, the retrofitting or revamping, sometimes called modernizing, of ammonia converters. It provided an opportunity for the redesigning of internals of existing converters, providing greater efficiency and reducing the environmental impact. Around 1980, Ammonia Casale came back into the picture. For many years after the Second World War, it had been in the doldrums, but a group of engineers at Ammonia Casale around 1980 developed new internals for use in Kellogg, Chemico, and other aged reactors. This is the axial radial converter developed at Ammonia Casale, which brought it back to the forefront in the development of ammonia technologies. A few years later, Ammonia Casale engineers developed a plate converter, which was important in the production of urea. And subsequently, Casale moved on to the design of grassroot plants and converted hundreds of converters using its new technologies. In April 2021, 100 years after its foundation, Casale joined a consortium of American research institutes to develop an ammonia plant for the production of green hydrogen. This project will demonstrate efficient production, it is hoped, of hydrogen by electrolysis. And of course, this will be a major contribution to sustainable growth and the world food supply. The return to electrolysis is interesting insofar as this is exactly where Luigi Casale started out in 1921. So, have we come to the end of the United Kingdom synthetic ammonia industry? I raise this question because of the current situation. The former ICI factory is now a division of CF Industries of Deerfield in Illinois, which on September the 15th announced that operation will be halted due to high natural gas prices. Well, at this moment, we don't know. It may be that the company will receive subsidies or assistance from the government to continue operations in the near future, but it may be otherwise. Also, we can ask, is this the end of the Haber-Bosch process? Insofar as there are several difficulties and it's extremely expensive and energy consuming process. There have been many investigations, some going back to the 1920s, on nitrogen fixation using bacteria. And a lot of work was done at the University of Sussex in the 1990s. There also have been studies into catalytic electrochemical nitrogen reduction, but neither of these methods have produced results that can be even remotely considered viable for industrial use. So to conclude, the global expansion of the ammonia industry began with the availability in 1921 of Casale's invention. Hydrogen is the most important cost item. From around 1940, it was increasingly produced from natural gas. High-capacity ammonia units were introduced by Kellogg from the mid-60s. India, China, and the Soviet Union emerged as the leading global producers of ammonia. As a result of the introduction of new ammonia technologies, Indian food production increased from 50 million tons in 1950-51 to 152.4 million tons in 1984-85. China today is the global leader. In fact, during the period from 1970 to 1980, it contributed to doubling of global ammonia capacity. And thank you for listening, and also to these corporations.
Thank you very much indeed, Tony. And may I just mention that at the very beginning of your lecture, but unfortunately I wasn't really sort of able to break in, Robert Lynn sent from Sky News that CF Industries has now resumed production of ammonia, and therefore, more importantly at the moment, the production of carbon dioxide. So it looks like if we've been saved, and all the carbon dioxide that we need will come once again into supply. So that's a sort of very topical ending to your talk, and I've been able to answer the question you posed at the very end, perhaps only temporarily, but we'll see. And I know that for everybody will be watching the news very avidly to find out what the latest situation is. Perhaps before I start with the question, and we've only got two so far, both of them from me, but before I start with my question, I could perhaps give a little anecdote of myself. I went to Erosion, I hope I'm pronouncing that properly, which is the big Yara ammonia plant, which is more famous for the production of heavy water, which it still does, in fact, although they try to deny it. I did see plenty of deuterium cylinders around the plant. But anyway, that's not really the point of my talk, my sort of little story. The thing was that I asked for some catalyst to take back to the Science Museum to add to the Science Museum collection. So they took some what looked like grey pellets. It looked a bit like graphite, actually. They sort of put a handful of grey pellets into an envelope and gave them to me. But then the sort of safety person at the plant insisted that I would also given a very large HazChem label to go with it. So when I got back to Oslo, I sort of started to get a bit worried, firstly about showing this HazChem label to the airline, because I suspected they probably wouldn't let me on the plane with the sets of labels. Warm in my pocket. And I was a little bit worried it might be pyrophoric. So I called up the company, Yara, and I said, I don't have an awful feeling they're not going to let me on the plane. So they said, oh dear. So I said, well, what should I do with it? And they said, are you there, Oslo? Tony, are you there?
Yes, unfortunately, you froze for about a minute, so I didn't hear everything you said about what the company advised you to do.
Well, anyway, we're back here again. So when I was saying what, they said to me, are you near Oslo Harbour? And I said, yes. And they said, oh, just throw it into the water then and forget about it. So that would be the end of my sample of ammonia Haber-Bosch catalyst. Anyway, the two questions, in fact, we might have a third. The two questions I've got is, and they're both from me actually. Where did India's natural gas come from?
It came in around 1970s. I think the Bay of there were two major finds. I think one in the Bay of Bombay.
Okay.
I think the first one of the first large factories was opened by Mrs. Gandhi in 1974, based on, again, Kellogg technology, and that was I believe, the very first Indian factory based on natural gas as feedstock.
But where did they get the natural gas come from?
The Bay of Bombay. I think there were two major finds at that time.
Okay.
At that time.
Now, my second question is somewhat related to the previous one, but surely if the Russian or Soviet, if you prefer, the Soviet ammonia plant were being paid for by the import of urea and ammonia from the same plant to America, wasn't that undermining the American industry?
Absolutely, that was the major problem. I think in Louisiana, about 1998, there were about 10 members of a consortium interested in ammonia synthesis, more like an association. Within about 2 years, there was only one left, CF Industries. This was a major problem for the Americans. In fact, there was a major report commissioned by the US government into this particular problem.
What, of import from other countries, in other words?
Yeah, imports and the impact on the American industry.
Yeah. Okay, well, Tony, your talk seems to have been so good, but it hasn't attracted any questions, which is the kind of talk we want. And I'm just mentioning passing, but Mike Juris mentioned that you talked about the ICI acquisition of information after World War I, and he points out the acquisition of technical information by the sort of Fiat and Tyros and Bios after World War II. So, you know, there would be captures of information after both World Wars. It's just a comment.
Yeah, however, there was some information of use to the ammonia industry outside Germany after the Second World War, but it was minimal compared with all the other new processes of polymers, plastics, and such like that was coming out of Germany. The information.
That's my impression as well. Yeah. Okay. Well, thank you very much, Tony. Once again, a fantastic talk, and we look forward to another fantastic talk on the ordeal point, which well, I think we'll leave for next time. So tune in next month for a talk about the ordeal poison and the connection with anesthesia. Tony, once again, thank you very much. And
thank you, everybody, for listening.
Yes, and I was just going to say that. Thank you very much, everybody, for listening. And keep well and keep safe. Bye for now.
Bye.